Good morning, everyone, and welcome to today's webinar, Integrating 3D Sand Printing Technologies into Traditional Foundry Tooling Processes. I am Shannon Wetzel, Managing Editor of Modern Casting and Metal Casting Design and Purchasing magazines, and we have a fantastic webinar for everyone today with two speakers from Craft, Pattern, and Mold. Before I introduce them, I want to go over a couple of housekeeping items. First, this webinar will be recorded and made available to today's attendees. You will receive an email with a link to the recording within a week after the webinar. Second, the presenters will be answering questions at the end of the session. You may type your questions in at any time during the webinar in the question box in your webinar control panel. And now let me introduce our speakers, Tony Kramers and Steve Shade. Tony is the President and CEO of Craft, Pattern, and Mold. Starting in the foundry at the age of 16, Tony has been working in the metal casting industry for over 35 years. He received his pattern maker certificate from the Minneapolis Vocational Institute and started as a pattern maker at Craft in 1991, eventually advancing to the position of project manager and inside sales. Since acquiring Craft Pattern in 2008, Tony has expanded the operation by investing heavily in cutting-edge CAD/CAM technologies, CNC machining, CMM inspection, and foundry equipment upgrades. Steve is the project manager at Craft Pattern. He earned a BS degree in manufacturing engineering from the University of Wisconsin-Stout in 1998. While in school, he interned at an iron foundry and was eventually hired full-time after graduation to the position of manufacturing and inside sales engineer. In 2007, he was hired by Craft as the project manager to oversee the tooling, machining, casting, and prototyping operations. In addition to project management duties, specific areas of focus and expertise include gating and risering systems, ferrous and non-ferrous alloy process development, CNC machining, CMM inspection, and NDT methods and techniques. So, if everyone's ready, we'll get this thing started while I turn it over to Tony to begin.
Okay, thank you, Shannon. And hello and welcome, everybody. Thank you for joining us today. My name is Tony Kramers, President of Craft, Pattern, and Mold. The topic of our webinar is going to be who will be our next president of Trump or Hillary. No, I'm just kidding. That's next week. So back to our actual topic for this webinar is integrated 3D sand printing with traditional foundry tooling. Today we are going to focus on three main points. First, how to decide when the use of 3D printed sand molds and cores is appropriate in your process. Second, how to navigate the cost curve with 3D printing. Final, incorporating the use of printed molds, cores into your existing process. So, let's get started. First, let's talk a little bit about casting history. Consider how far foundry technology has come in just about in the last 100 years. Up until the 1930s, most of the melting was done using fossil fuel-based systems, namely gas and cupola. Today, those technologies are still being employed, but the electric melting system dominates the landscape. Foundrymen used to make prepared sand or green sand, manually adding clay and water by hand. Molding technologies was limited to the skilled tradesmen using manual squeezers and floor molding lines, both which are still used today. And patterns were typically made of wood materials by trained craftsmen that spent years perfecting their trade. Fast forward into today, where technology was delivered fully integrated PLC control systems and computer automated molding lines that can produce hundreds of molds an hour. What used to take a team of pattern makers weeks and months to build can now be accomplished by a handful of people in a matter of days. Pattern makers today are skilled CAD/CAM technicians with the ability to program, set up, and run complex CNC machines. And now, with the advent of 3D sand printing, we have a toolingless process where cores and molds are directly produced from 3D CAD geometry. There are even machines out there today, EMLS machines, directly 3D printing metal parts. Yes, a 3D metal casting or not a casting, depending on how you want to look at it. Regardless, it's truly amazing what technology has been able to deliver in such a short amount of time. While the technology used to produce tooling and sand casting has changed over the time, the basic principles behind their manufacturing has not. You'll still need parting, draft to make a mold. Although 3D printing is certainly challenging the mindset. Generally speaking, foundry tooling is developed using a series of 4 to 5 interrelated steps. First, the engineering, where you address everything related to the casting, covering both the end customer and the foundry's needs. Tool design. Once the part is designed, locked, the tool design can begin. A lot of software and technology advancements in the recent years have been a big impact on this area of process. Solidification modeling probably being the most influential. From there, the pattern impression and the core box cavity are cut. Then gating is added to the pattern tooling rig to run on a molding line or a core machine of choice. Lastly, the tool undergoes some sort of validation, which could be as extensive as a dimensional layout or a laser scan tool back to the 3D file, to a full-blown capability study performed at the molding line. Some customers may just require a handful of samples for a sign-off, but the bottom line is the customer requirements are going to drive the amount of validation that is needed. No longer considered a commodity, engineered cast components need to compete with other processes on the basis of design flexibility, process capabilities, timeliness, and the cost effectiveness. Tools need to ensure that castings produced will meet the needs of not only the end customer, but the needs of the stakeholder, the pattern shop, the foundry, machine houses, etc. Because of this, tooling should be thought as an income-generating asset, not a cost center. Getting the tooling right the first time and producing good parts take time, effort, and money, but an investment that may pay huge dividends. Recognize that the tooling is not cheap and takes time to produce. It's typically built to run on a selected group of machines. So transferring to another foundry with another molding equipment may prove difficult and costly. If you want to start an argument with a foundry owner, just ask them about the cost of storing tooling. So how can we eliminate or at least minimize the negatives associated with tooling? One is by leveraging the technology, and what I am referring to is the use of 3D printing. Its fixed cost is borne in the engineering phase of the tooling build, so there is no physical tooling needed and the direct cost is very level, as we will soon discuss. We don't use technology which includes 3D printing just because it's new and cool. We use it to solve problems in a better way. Does digitalization solve all of our casting problems? No, not even close, but it's an available option and it's a good starting point. 3D sand printing can do a lot of unique things for the foundry. Beyond that time compression, it can offer a more cost-effective, innovative way of doing things. There are cast geometries which, until recently, were simply not able to produce due to traditional tooling limitations. 3D sand printing has taken off the cuffs in those instances and given the designer and the foundryman a new tool which can be used to solve difficult challenge problems. However, 3D printing is not the be-all, end-all solution we want it to be. There are limitations. There are certain situations where it just won't work, whether the reason is cost, quantity, lead time, or quality related. The technology as it exists today does have limits. It's getting there, but just not ready to compete with many of the tooled casting processes on a mass scale. So this webinar is about the integration of 3D printing with tooling processes. For the sake of time, we won't get into the technical aspects of 3D sand printing. I assume everyone has at least a base level of understanding with this process. There is a wealth of information out there on the internet about the technology, videos, and technical data, so I encourage you to check that out if interested. So here we come to the heart of the matter. Every metal caster is in business to make money. If not, it's considered by the IRS to be a hobby, and in that case, you really have is an expensive and stressful pastime, as many foundrymen can attest. So what does it cost to 3D print sand molds or cores? Well, to start with, the capital equipment required is very expensive, and it's difficult for all but the largest, most specialized foundries to consider. To solve this availability problem, there is a number of service bureaus set up around the United States and around the world, for that matter, dedicated to producing printed molds and cores for foundries. All that is required from the pattern shops or foundries is a 3D CAD file they can use to print whatever you want. The cost, which is typically calculated as dollars or cents per cubic inch of the build volume, is directly related to the mold or the core size envelope, length, width, or height. Therefore, it's extremely important to consider the scope of what you are trying to accomplish with the use of 3D printing. We cannot cost-effectively print large cores when competing basic tooling processes. There has to be an edge, a competitive advantage offered by 3D printing in order to make it a viable option. So what does that mean? It means that 3D sand printing has matured into a complementary process that can, under the right circumstances, be viably integrated with traditionally foundry tooling and molding process to yield beneficial results. It's a great technology, but it has to be used in the right situation, under the right circumstances, for the benefits to be realized. So, what are the right circumstances? At this point, Steve will continue our discussion of the topic, and thank you. And here is Steve Shade.
Hello, I'm Steve Shade, Project Manager at Craft Pattern and Mold. To determine what is right for a particular casting application, we need to understand and analyze the concept of the cost curve. What is that, you ask? Well, in simplified terms, it's the relationship between part production volume and total program cost. For our discussion purposes, considering we're generally dealing with lower production volumes and prototypes, we'll consider it a linear relationship. Now, we all remember from high school algebra that the equation of a line is y equals mx plus b, where m is the slope of the line and b is the y-intercept. In casting terms, b is the fixed upfront cost of a project, which is usually tooling or engineering cost. M is the individual casting cost, x is the total number of parts being produced, and y is the total program cost. The cost curve for a typical casting made with tooling might look something like the graph shown, The fixed cost and the per part cost will vary greatly depending on the needs of the individual casting and foundry producing the part. In a high volume situation, the cost curve for that same casting would likely be flatter. The tooling might be very expensive relative to the other casting options, but the piece part cost would benefit, and so the overall cost of the program will be much lower in the long term. Conversely, if relatively few parts were needed, then a simplified tool capable of running on less automated equipment might suffice and be more cost effective from a program cost standpoint. How about the cost curve for a part that is produced with a 3D printed mold versus with tooling? The fixed cost, the tooling, is significantly reduced and for the most part is constrained to engineering and CAD cost. The 3D printing curve shows the per part cost being relatively high compared to the same part produced using tooling. So at lower volumes, this is a very viable method of producing castings. Of course, the actual numbers will vary greatly depending on the size of the part and geometry. Now, what if we were some way able to optimize the mold size and print a smaller envelope? The slope of the line, the per part cost, would change favorably. Rotating the parting orientation, breaking the mold components into smaller pieces or combining pieces, and minimizing offsets can all be used to reduce 3D printing cost and move the break-even point out. The key take here is the break-even point is variable for each casting and highly dependent on the skill, experience, and abilities of the CAD operator to optimize the mold for printing. Our team of CAD/CAM engineers at Craft can help you navigate this process. Besides printing an entire 3D mold, let's look at another option, the hybrid concept. How can we maximize the benefit offered by the technology to produce castings at the most time and cost-effective levels? The short answer is, it really depends on the part. I know, nice non-answer, right? For a complex part, without draft or with significant numbers of cores and or undercuts, we can 3D print portions of the mold that give us the most headaches from a tool design, cost, or feasibility standpoint. These mold inserts, or core packages, are used very much like a core. There is still a physical pattern to produce the non-geometry areas of the mold, but the part features are encapsulated within the mold insert. The gigging and mold locks, and maybe even some of the casting features, are produced with the pattern or by other cores. You will note the cost curve still has a fixed tooling component, the y-intercept, albeit at a lower cost than tooled options, and a piece part cost, the slope of the line associated with it. The piece part cost using this hybrid approach can be less than, equal to, or greater than the piece part cost of the tooled casting options. Again, it all comes down to the skill of the CAD designer and their ability to optimize the design for the 3D printing processes and tooling. By optimizing the size and scope of the features to be printed, and by taking further advantage of tool shortcomings and weaknesses, 3D printing options can become a very viable tool for the foundry. Think about it this way. 3D printing needs to be able to bring something to the table other than being just another cool technology. You need to have an advantage over the tool processes. There is the obvious advantage that 3D printers don't care about draft and parting. They don't. And foundries need to accept that. It is probably the #1 reason for 3D printing success. If you have a customer who absolutely refuses to yield on a parting line or draft issue, you really need to be considering 3D printing as a possible solution. The ability to eliminate tooling is another advantage. It's a great option for small and prototype quantities to keep total project costs down. How about a complex core requiring loose pieces in a tool? Again, the 3D printer does not care what the geometry is. so this is another great opportunity for printing to shine. Core assemblies are another avenue in which 3D printing can compete with cores produced from tooling. Instead of having multiple tools and fixtures to produce a core assembly, a singular 3D printed core may be a more cost-effective, accurate, and reliable option. Remember, cost is a function of the build envelope size. So if you have a relatively small core that takes up a significant amount of real estate, it is still going to be an expensive core to produce. Conversely, a heavy but compact core may be a cost-effective 3D print option depending on the situation. The trick is to find the weaknesses in the tooled option and to evaluate the ways in which 3D sand printing can possibly be of benefit. So, how does Craft decide how, when, and where to use 3D printed molds and cores? We're going to run through a case study example today using the tools and methods we've discussed and apply it to an existing casting we are currently prototyping for a customer. I would like to thank TerraDrive Systems of South Brookston, Indiana for granting us permission to use this part as a case study today. Here's the casting we have been presented with. It's a fairly heavy sectioned 8050-506 ductile iron sand casting. The final part will have a number of machined surfaces, ports, and cavities, some of which will connect to internal core passages. The total number of finished machined castings for purposes of this prototype project is 6 pieces. That's the life of the program. The coring of the raw casting is fairly straightforward. The core geometry is simple and could be produced in virtually any modern core process. The problem is there's only one area where the core exits the casting, which is where the core would be set into the mold. This would dictate the cope and drag parting orientation as shown on the slide. This may or may not be a concern depending on how we elect to make the casting. Without a second point of registration, the core is essentially free to do as it wants. We can control the core rotation by altering the core print shape, but we can't control the location of the core from cope to drag very well, especially in iron. The other issue is the 2 fingers coming off the core deep inside the casting will be potential failure points. They are relatively thin and extend out a fair amount from the main pin core body. The fear is they will yield under the heat of the metal and float towards the cope surface, or in a worst case scenario, break off completely. So, how do we address this? Taking a closer look at the final machined part geometry, we can see that several large port diameters are machined into the casting that ultimately intersect with the 2 areas of concern. If we add machine stock to those port features and integrate them with the original core geometry, we are able to tie the core assembly to the outside of the part in 2 additional locations. This will greatly help to maintain core location, stability, and integrity. However, this does present several issues. First, the core would be difficult to handle and prone to breakage. Second, the core may or may not be producible using tooling due to undercuts and core locked features. And lastly, the new core prints may effectively blind the optimal riser contact surfaces on the back side of the casting. So, what are our options? One, we could build traditional pattern and core box tooling. The pattern is pretty much open and shut, so the 3D printing process does not offer any distinct advantages over the tooled option with respect to the pattern. However, the core is complex and will require multiple tools and possibly an assembly fixture, which is not very favorable at low volumes. This option has the longest lead time and most upfront costs due to the amount of tooling involved. Option 2, we can forgo tooling altogether and 3D print the entire mold and core package, but as previously discussed, this is only viable if the quantities are low enough, which is not the case in this situation. And 3, we can utilize the hybrid concept discussed, machining a traditional cope and drag pattern tool that utilizes a 3D printed core. The complexity of the core is thereby neutralized as a cost driver, resulting in the most favorable economic solution from a core standpoint. Analyzing the cost curves for the various options presented, we can see that at the low production quantity of just 6 pieces, the most cost-effective option is to CNC cut a pattern and 3D print the cores. Reference the green line on the graph. The 100% 3D printed option, shown in orange, would be the most cost-effective at very low quantities, perhaps 1 or 2 pieces. This is a very good method of constraining total project cost if all you need is a part or 2. CNC machining an insert pattern and then using 3D printed mold inserts and cores is also a good option for very low quantities or for difficult to tool pattern geometries. There is a fixed cost related to the tool, but it is minimal compared with the other tooled options. Lastly, the tooled option offers the best piece part cost, but has a relatively high fixed cost in this case. And so the break-even point between that and the most cost-effective option is several times higher than the project quantity of just 6 pieces. Now, I should point out that the final core geometry developed for this project meets our process needs for prototyping while satisfying the customer's end casting requirements. But it should not be considered the one and only possible solution. In a production setting, this design may or may not be desirable, depending on a specific foundry's capabilities. While the core is not overly complex, the core as designed will need to be made in several pieces and assembled if tooled options are utilized. However, as we saw in the previous slide, the 3D printed core used with the CNC machine pattern yields the best cost for this project. It is worth noting that with some optimization and streamlining, there is the potential for the 3D printed core to be produced at a discount to tooled options. In this case, the 3D printed core would become the long-term solution and offer the lowest cost of manufacture over the lifetime of the program. Not only is the tooling and casting cost less, there is no core box tooling to maintain, and the time to market would be reduced with less tooling required. Changes to the core would be confined to CAD modifications only. Different iterations of a casting or prototypes could be trialed with virtually no impact to tooling or disruption of casting production. This is a very powerful point to consider. So, to summarize, here is how the part was produced. We CNC machined the cope and drag patterns for use with our air set molding lines. After a quick dip and a ceramic coating, the 3D cores were set in the mold as you would with any other core. And here's the resulting ductile iron casting poured in our foundry. The top riser, an insulated neck-down riser sleeve placed on top of the casting, was connected to the casting through the 3D printed core. Overall, we were very pleased with the results. We've covered a lot of information today, and I hope you gained some insight and thought into how 3D printing can be integrated with traditional foundry tooling to produce real-world results. To summarize, we discussed the various combinations and options available to the foundryman and toolmaker to make a casting. Tooled, 3D printed, and hybrid options were presented and discussed. The cost curve concept presented is nothing more than simple break-even analysis, economics 101 stuff. The important thing to gain from the exercise is to be open to ideas and concepts that, until recently, have been suppressed by limitations of what tooling could offer. Craft has been working with 3D printed parts for over 20 years. We look for ways to incorporate the use of 3D printing into projects where it adds value and makes sense. If you have a part that might benefit from 3D printing, please feel free to contact us to discuss your project. Our team will be more than happy to discuss your needs and how we can be of service. Thank you for your time attending the webinar today. At this point, we'll turn to the open forum and answer any questions you might have.
Thank you very much, Steve and Tony. Great presentation. And yes, for all you attendees, if you have any questions, please type them in the question box. So we've got a few that came in already during the presentation, so Tony and Steve will get started. One question we had, you know, in the case study you gave was for a 3D sand printed core. What other materials have you worked with for the 3D printing, and is the kind of the cost model similar, or what's your experience been with other materials?
Yeah, the plastics are probably kind of the same cost. Other types of materials, I mean, if you're asking about metal alloys, I mean, with aluminum, your low carbon steels and irons, we pretty much have worked with all of those here in the past, and they've all worked very well. The aluminum side is probably one that has probably by far the most cores assembly, where you can kind of see a lot of that being more of a beneficial area for the 3D printing of a core assembly. But there is some value too, also, just like what Steve was showing here on that one iron part, where there's limitations on how to support the core, or just to be able to manufacture it.
Some of the other technologies that are used with 3D printing, I mentioned we've been using printing processes for over 20 years. That would include SLA, SLS, FDM. There's a host of technologies on the market today. The cost structure is very similar with 3D sand printing to those plastic printing processes, in that cost is usually a function of overall build volume. So there's a time component there used to build the part, but then there's also material costs involved. It's not going to be a one-to-one equation between a plastics and a 3D sand printing part, but the concept is still the same.
Thank you very much. The next question is, what industries are you seeing this technology being utilized in most?
Well, obviously, 3D sand printing is confined primarily to the foundry industry, but within the foundry industry, we've seen it utilized in virtually every end-use application you can think of. It's not constrained to any specific alloys or different industries, you know, agricultural, automotive.
Yeah, the 3D printing,
it's in every industry that we've seen.
Yeah, I mean, the 3D printing technology, it really does wrap around originally the rapid prototyping process. You know, I mean, obviously that was the kind of the big game changer, is to try to get something in your hand quicker and faster. With the 3D sand printing, you start stepping back and looking at that it's a tool. It's a tool for in a lot of different cases. For prototyping, you can get stuff, quicker results, and then also you also can realize too it can be very valuable in the production world. That's what I've seen here in the last year, where production foundries are able to utilize that in their production line and be able to save money and cost and time.
Thank you. We're also getting a lot of questions about, one, if you're printing them in-house or getting them from another source, and then two, what types of sand and binders are used within the sand?
To answer that question, no, we do not have a 3D printer in-house. We are utilizing the service bureaus that are out there today that will take our file, our design of that core or mold package, 3D print it, ship it into us, and then we would integrate that in with our processes, namely into the molding line to make them final mold and pour the casting.
And then do you know what kind of sand is it? Specific?
I'm sorry. Yeah, the second part of your question, the type of sand that's used, it's an AFS, I believe, 70 to 80 grain fineness silica sand using a furan-based binder system. That's primarily what we have utilized. I know there are other systems being developed out there by other companies that are trying to use different resins, maybe sand additives to control veining, gas defects, things like that. And that's the next generation of this technology.
With the capabilities of 3D printing sand, I mean, you're able to put these cores or mold assemblies into a green sand molding operation, or you're into a dry set or air set. What we have here, what we utilize it for, is the core assemblies in our PEP set urethane, phenolic urethane operation here at Craft. It works out very well. There's no issues with the materials when the metal pour against it.
Okay, thank you. And what software are you using to do the CAD modeling?
Well, that's a good question. Being in the prototyping business, we work with a lot of different customers that have different capabilities and software packages. The most common are probably SolidWorks and Pro-E. We have seats of those in-house. We also utilize SpaceClaim, which is a relatively new player in the market for some of the CAD. We have surface modeling capabilities with several softwares to include PowerShape from Delcam and also SurfCam. So we're very CAD heavy. The main thing with 3D printing, like with sand and with other 3D printing processes, is to have a clean file. So we like to start with a solid model, and Pro-E and SolidWorks are very good at doing that. There are also other software platforms out there that customers use that integrate very well with the software we have in-house. So we're able to utilize pretty much anything, you know, today as it comes in the door, and be able to generate files that are clean to be used for 3D printing.
I guess going back to some of the stuff that we talked about earlier too, that kind of ties to this, that 3D CAD file, if it was being created by the pattern shop, you know, for the foundry, it's another asset or another tool, just like the pattern tool is. So if there is reorders and stuff like that, the pattern shop will be able to give you that file so you can reuse it over and over again. So that's a nice bonus part on that part.
Thanks, guys. We've got a lot of questions coming in. We won't be able to get to them all, but we'll try our best. So are you able to add chills or other extra tools when you're using a 3D printed core or mold?
Yes, we've used chills with the 3D printed cores. You just have to plan for it on the front end. You'd have to leave a pocket for that chill to be inserted, either from the A side or the mold side, or the back side of the mold, where you could drop it in from the back and maybe backfill it with sand or glue it in place. So that's very common, especially in the aluminum applications. Inserts, I think one area I can think of off the top of my head would be maybe an aluminum casting that might have an iron or a steel bearing insert that can easily be integrated with this process as well.
Great. Another question we got a few times is what would be like the size limitations or the dimensions for 3D printed technology for molds or cores? I know that you don't have the printer there.
Right. Well, there are different size machines, but that's really not a factor because molds can be broken into a variety of components. If you had a mold that was, to exaggerate, 10 feet long, you could build it in sections and assemble them like Legos. So that's really not a limiting factor. To do so from a cost standpoint would be extremely expensive. But it can be done if it's a one-off and tooling is not desirable.
And that kind of leads to another question. The sample that you showed was a project of six castings, and you mentioned the one-offs. But what if you were more in a production of, say, 40 castings? Would there be an instance where the 3D printing or the hybrid process could be a good option, and what kind of would need to happen to have that be a good tool or a good?
Absolutely, and that's kind of what we're talking about with the optimization. If we get to a point where we can constrain the size of that core, which relates to the cost of the core, to a point where we have a favorable situation in that the 3D printed cost is lower than the total cost of production of a core or even a core assembly, then certainly we have a situation where that can be the long-term solution. I think the biggest advantage would be not design-related problems that you're solving with 3D, because tooling can usually come up with a solution for those situations. But where you get into situations where you might have multiple cores and paste fixtures, you might have 2, 3, 4 core boxes or more. You might have paste fixtures. You're going to have variation with those cores. It's very time-consuming. The scrap rate might be higher. A 3D printed core, in that case, might be a very economically sound choice.
Thanks, Steve. And just a reminder to the attendees still here that there will be a recorded version of the webinar emailed to everyone, so you'll have that for your use later in your reference. We'll probably have 2 or 3 more questions here. First, what kind of dimensional accuracy are you expecting from your 3D printed cores or molds? Is it similar, different than your traditional?
We've seen similar accuracy to what you can get off of a tool. It's been very good. I mean, dimensionally speaking, X, Y, and Z, those are factors that need to be controlled by the 3D printer, and I think the service bureaus out there have done a pretty good job of dialing in their machines and ensuring that what you expect to get is what you actually receive.
Okay, and then how about the handling or transferring of cores? Anything special that you guys do to avoid core breakage?
It's similar to anyone that's buying cores at an outside shop. I mean, they have to be packaged, securely. Yeah, different ways, and so that they're secure and not able to be damaged. Probably, I don't see a lot of breakage in shipments because of the core being fragile. Usually it's damage from the freight company, a forklift operator, or stacking pallets of cores. That's usually the bigger issue. But there again, that's the same thing you're going to have with any product. Yeah, with any product. And like I said, if you use an outside core shop, that's still going to be the situation. So it can be addressed.
Great, thank you. And then can you talk a little bit about how the surface finish compares to a traditional sand core?
Yeah, the core, the finish, like all 3D printing processes, is usually the biggest issue designers or end users might have. you do notice that it's made in a different process. It's rougher. We've kind of got around that in some ways by utilizing different mold coatings, but in general, you're still going to have a rougher surface. I don't know that that's really too big of an issue in our situation with dealing with prototype parts. Usually they're being developed for some sort of a functional test where they're trying to prove out a design or a material concept. So in a production setting, yeah, I could see where that's a problem. In certain pump applications where you need to have a nice smooth surface, you can't have a rough surface that might introduce cavitation or flow problems. That is certainly a concern. But again, I think if you work with your coating supplier, you could probably develop a process that could mitigate that issue.
Primary is just because how it's built with a 3D printing, plastic or metal or sand. They all have build lines, kind of a staircase. Those are the areas that you have to kind of determine on if it's something that needs to be addressed for a surface finish call out.
Thank you. I think we have time for one last question, and that is the issue of, I guess, sand removal after the casting's been poured. Have you been successful in removing the sand in the voided areas?
Yeah, it's no different than any other core binders or sand we're using in the process, other than it's generally finer than what we typically use in our molding process, and the resin levels are a little higher. But shakeout issue has been, there have been no issues related to that.
Very good. Well, thank you again, Tony and Steve, for today's webinar. And thank you to all the attendees for joining us. We will be sending you, again, the recorded webinar to you early next week. And then if you have any further questions, you see the email addresses there for Steve and Tony. And thank you again, Tony and Steve.
Thank you, and thanks everyone for attending.
Yeah, thank you very much.
All right, have a great day.